This is the oxalate ion, and we can form a Lewis structure using the periodic table, and from that Lewis structure we can actually predict what the geometry will be. So for the Lewis structure we have to count up how many electrons the elements want in their valence shell and how many electrons they actually have to start with in their valence shells. So if I look at the periodic table, I see that carbon is in this fourth row. So it's like 1, 2, 3, 4 over. So it's going to have 4 valence electrons. If I find oxygen, it's 1, 2, 3, 4, 5, 6 over. And they both want to have the electronic configurations of neon, which is 8 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8. They want to have octets. So with this in mind, we know that this carbon, for each of them, they have 4 electrons, valence electrons. For each oxygen, they have 6 valence electrons. And this 2- charge, that means we're going to end up having 2 extra electrons at the end in their valence shells. So since there's 2 carbons, I have to multiply that by 6. And since there's 4 oxygens, I have to multiply that by 4. This is the amount they actually have. So 2 times 4 is 8. Plus 4 times 6, that's 24, plus 2. So overall, that is 36? Sorry, 34, my bad. 34 valence electrons. How many do they want? Well, there's 1, 2, 3, 4, 5, 6 elements that all want an octet. So that's 6 times 8, that's 48. And how many is the difference? How many are going to be shared in bonding? Right. You subtract, you get 14. Now, of the valence electrons, there are 34 of them. If 14 are involved in bonding, how many are not bonding? Well, this is how many there are, right? And this is how many are involved in bonding, so how many aren't in bonding? Yeah. The ones that aren't involved in is just the difference between the total and the bonding electrons. Okay, so if there are 14 involved in bonding and each bond has 2 electrons in it, that means that there's 7 bonds. I just divide this number by 2 and I end up getting that there's 7 bonds. Okay, so I anticipate that I'm going to have 7 bonds. Also, I'm going to assume, and this is a pretty good assumption, that the central atoms in this thing are going to be carbons. Carbons can bond to each other, that they have 4 electrons, valence electrons, so they tend to usually be the center of stuff in organic molecules. It's a good place to start. So I would just draw in the valence electrons. I'm going to assume there's a lot of bonding, so I'm going to draw these electrons independently, not paired up yet. We'll pair them up at the end if there's pairs to be paired up. And then I'm going to draw an oxygen, actually 2 oxygens, near each carbon. And each of these has 6 electrons. 4 oxygens total, 2 around each carbon. I'm assuming there's symmetry in the molecule. And we'll see if that's reasonable or not. Okay, so I also have 2 more electrons, so I'm going to put 1 more on each carbon. The 2 more electrons come from the 2-. I almost forgot. So I'm just going to add 1 to each of these carbons.
So you don't add it to the oxygen?
I could have added it to the oxygen. I just threw them on the carbons because it's...
You can add it on any one?
Yes. Right now I'm just making sure I have them marked down. So I'm not adding them around anything more than 8. I tend to put them on things that have less electrons first. But there's no real reason why I couldn't put them around oxygens. But we'll start building bonds and seeing what happens. So right now we want to have, through bonding, 8 electrons around all of these elements. and none of them have 8 electrons. So there's an opportunity to build some bonds and start double counting some electrons. So I'm going to get rid of this electron on carbon and this one on oxygen and draw a bond. And actually I'm going to repeat this process 4 times over, once for every oxygen out there. So now that I've done that, I've made a bond out of an electron between each oxygen and its nearest carbon. I see that I still have 7 electrons around each oxygen. So I could start there. Actually, what I think I'm going to do first is I'm going to connect these 2 carbons with a bond so that they're all part of the same molecule. So that sounds like a good idea. I don't want this to end up being 2 different Lewis structures. I want it to be one. So I'm just going to put a bond there. Okay. So at this point, when I look at this, I see that there are 1, 2, 3 bonds around each carbon and a lone pair on carbon. So that's 8 electrons. So if I end up needing more bonds, I need to have 7 bonds and only have 5. These electrons are just not going to be on these carbons. They're going to be bonded to an oxygen somehow. So let me move those over. So I'm going to turn this lone pair into a bond. I'll put it on this oxygen. And I'm going to turn this lone pair into a bond. I'll put it on this oxygen. And let's see what we have. It's going to be kind of messy and wrong, but we'll check it out. We'll fix it. So now I do have 7 bonds. Hooray. I have 7 bonds. That's what I wanted. But this is weird and wrong. So check out this oxygen up here. It has 1, 2, 3, 4, 5 electrons, non-bonding, and then it has a bond, so that's 7 electrons total surrounding this oxygen. And that's messed up. Over here, this oxygen has 1, 2, 3, 4, 5 non-bonding electrons and 2 bonds. That's like 4 bonding electrons. That's 9 electrons total. That's messed up. So I'm just going to get rid of one of these electrons and put it on the other oxygen. So I'm swapping it from this one that used to have 9, which is too many. I'm going to put it on the one that didn't have enough. So I'm trying to make sure that I'm not like adding electrons. We'll double check at the end, but I just don't want to have that be an issue. I'm going to repeat the process over here. So this thing, this upper left oxygen has 1, 2, 3, 4, 5 non-bonding electrons and a bond, so that's 7. So this thing should have an extra non-bonding electron. I'm going to redraw them over on the other side, make it look cleaner. Okay. And then this should have an extra electron to have a full octet. I might have made a mistake somewhere in my hilarious attempt to draw this thing out. So by my count, this thing has 1, 2, 3, 4, 5, 6, 7 bonds, which is what we wanted. Let's make sure the number of electrons total is accurate. Or let's just do non-bonding. So there's supposed to be 20 non-bonding electrons. 1, 2, 3, 4, 5 pairs over here, and 1, 2, 3, 4, 5 pairs over there. So that's 10 pairs or 20 non-bonding electrons. If I add them together, I get 34 valence electrons, which is the right number of electrons. Let me make sure that I filled every octet, and if I have, then we're done. So there are 1, 2, 3, 4, 5, 6 non-bonding electrons around this oxygen, and this bond, which is 2 electrons. So that's 8 electrons surrounding it total. The same situation's over here on this upper right oxygen. Those have complete octets. These carbons each are surrounded by 1, 2, 3, 4 bonds. So that's 8 electrons surrounding each carbon, so those have a complete octet. And then these oxygens that are double bonded, they have 1, 2, 3, 4 non-bonding electrons, 2 bonds, so that's 4 bonding electrons. So that's 8 total valence electrons surrounding each oxygen that's double bonded. So again, this makes sense because it has an octet for every element. So to complete this, I have to indicate there's a charge, so I put a 2 minus outside the bracket, and this is the Lewis structure for oxalate. Notice that I made a mistake somehow. I don't even know where I did it. where I managed to lose an electron, but by truing up at the end with the counts that I started with, I was able to fix it. So if you do the math can help you repair the structure, and sometimes if you do the structure, it'll help uncover a error in your math. So putting these two techniques together is pretty useful, and it's almost Joe-proof. Let's take a look at this. If I was to guess what the geometry of this would be, like the geometry of everything around each of these carbons, I would first count how many things are around this carbon. So like there are no lone pairs around this carbon, but I see 3 bonded elements. It has an oxygen, another oxygen, and a carbon bonded to it. So it has 3 things around it. That's going to be a trigonal planar geometry. So it's going to be flat, like this O, this C, and this C are going to be in the same plane. And the bond angles here are going to be like 120. So that's going to be 120 degrees. The same geometry is going to apply to this carbon, so I expect both of these to be trigonal planar. They're both going to be in the same plane, I would assume. And we won't get into enough detail in this class to be able to tell you whether or not those 2 planes are going to be the same plane, but you should know from this class that the O, the C, the O, and this C are going to be in a plane, and that the O, the C, the O, and this C are going to be in a plane, and that they should be about 120 degrees for all the bond angles here. Let's go take a look at what this looks like with a nice 3D modeling applet online. So here's the oxalate ion that they generated in this software, and I had to use oxalic acid, I think it's called, where you have, instead of an O minus here, you have an OH. But the geometry between the carbon, the oxygen, and the oxygen will be the same. And as you can clearly see, that geometry from here to here to here to here, it's a plane. Those 3 things are all in a plane together. And the symmetry of the molecule would dictate that would be the same for either carbon, but you can see it here as well. They're in the plane as well. So that's a 120 degree angle. 120 degree angle between OCC and OCO. It's not a tetrahedron. You're not looking at something that's square, that's tetrahedral, or that's trigonal pyramidal. This thing's pretty flat. If I go to Wikipedia, yeah, it looks kind of flat too. So our model for geometries based on valence electron pair repulsion, the Vesper model actually worked out pretty well here, and that's how you can create the Lewis structure and predict the geometry of this molecule.